Imagine the birth of our sun, an occurrence that took place approximately 46 billion years ago in a solar nebula. Nebulas are the birthplaces of stars, the celestial bodies that illuminate our night sky. Stars, which resemble enormous spheres of fire, actually contain a delicate equilibrium between the forces of gravity and thermal pressure. This equilibrium, called hydrostatic equilibrium, is what maintains stars stable for the majority of their lives. However, when this equilibrium is disturbed, there are only a handful of forces that govern the birth, life, and death of stars. Beyond gravity and thermal pressure, there is the powerful, strong nuclear force and the elusive, weak nuclear force. Together, these forces shape everything in our universe. Every time scientists discover a new force, it reshapes civilization and redirects humanity's path, just like Newton's revelation. Einstein's revolutionary E equals mc squared revealed the energy that powers stars and solved the mystery of nuclear forces. The work of Faraday and Maxwell, who discovered the laws of electricity and magnetism, led to the development of motors and the advent of instantaneous communication through radio and television. And finally, the work of Schrödinger, Heisenberg, and others who deciphered the code of quantum theory. In the last 100 years, scientists have discovered two basic characteristics shared by all forces. Firstly, all forces are carried by specific particles or bundles of particles. For example, the electromagnetic force is transmitted by photons, while weak bosons and gluons are responsible for the weak and strong forces, respectively. By 1984, these particles have been extensively studied, but the graviton still remained. Second, just as mass dictates how gravity acts on an object, so too do the specific charges that particles possess, which govern their interactions with the strong and weak forces. However, the exact reasons behind these charges and masses are still a mystery. Einstein sought to develop a theory that would integrate all these forces into a single framework, which he called the unified field theory. He envisioned a simple equation that would allow him to understand the mind of God. Even Einstein failed to do it. However, science is getting closer to a theory that could unite the four forces of nature into a single framework. This theory could solve some of science's deepest mysteries, like what happened before the Big Bang, what caused it, what's beyond a black hole, and many more. It's now famously called the theory of everything. Come along on this mysterious journey with me as I unveil the theory of everything. Looking up at the twinkling stars in the night sky makes one wonder if there's a higher power at work or if everything is just a random collection of chance occurrences. The ancient Greeks were pioneers in this search for order in nature, with thinkers like Aristotle proposing the idea that everything is made up of four basic elements: earth, air, fire, and water. However, how could these elements explain the bizarre phenomena they observed? The intricacy of our environment has always fascinated Greek philosophers, who put forth deep ideas like the idea that everything is composed of indestructible atoms and the possibility that the diversity of nature can be explained by the mathematics of vibrations. However, a few centuries later, Galileo Galilei emerged, challenging these established views. Galileo gave us a better telescope, which allowed us to peer deeper into space, and he also contributed to the scientific method. His groundbreaking work in mechanics and motion would later lay the groundwork for modern physics. Despite facing criticism, Galileo's defense of the heliocentric model of the universe was revolutionary. Despite his unhappiness, Galileo passed away in 1642, but his legacies continued to pave the way for future discoveries. In the same year, a child named Sir Isaac Newton was born across the English Channel, and he would eventually finish Galileo's work by combining Galileo's and Newton's contributions to unified cosmic understanding. Inspired by Johannes Kepler's theories, Isaac Newton published his magnum opus, Philosophiae Naturalis Principia Mathematica, in 1687. This seminal work established the groundwork for classical mechanics, introduced Newton's laws of motion, and revealed the law of universal gravitation. Through this publication, the world learned about one of the most fundamental forces in nature, the gravitational force. As a seemingly insignificant force, it can unleash the most destructive object in the universe, the black hole. Black holes, we encounter this force constantly. One important feature of Newton's law of motion was its generalizability. It could be used to calculate the revolutions of both small objects, like spheres, and large ones, like planets. However, astronomers in the 19th century noticed an unusual astronomical anomaly. Uranus's orbit was not following a perfectly elliptical path as predicted by Newton's laws. Uranus's orbit wobbled slightly, leading scientists to consider two possibilities. Either Newton's laws were incomplete or the gravity of an undiscovered planet was influencing it. The discovery of Neptune solidified the validity of Newton's law. Michael Faraday, another scientist without a formal education, went on to discover a fundamental force. He demonstrated that moving a magnet inside a loop of wire generates electricity, which was a groundbreaking observation during a time when the relationship between electricity and... In his early years, the concept of magnetism was unknown. However, as time went on, Faraday realized that a moving electric field could produce a magnetic field. Despite his lack of formal education, he was able to describe his discoveries mathematically by drawing strange diagrams in his notebooks, which resembled the patterns created by iron filings around a magnet. Faraday also introduced the idea of a field, which is one of lines of force that extend throughout space form fields. For example, magnetic fields encircle all magnets. The Earth's magnetic field, for example, begins at the North Pole and travels all the way to the south. Even Newton's theory of gravity can be modeled as a field, with the Earth's rotation around the Sun creating a gravitational field. Faraday's discovery helped to explain where the Earth's magnetic field originates. A new branch of mathematics, vector calculus, was formalized by James Clerk Maxwell. Kepler and Galileo laid the groundwork for Newtonian physics, while Farr's work set the stage for Maxwell's equations. The constant movement of charges inside the Earth generates the magnetic field. Newton proved that objects move due to forces that can be described using calculus, while Faraday proved that electricity moves because it is driven by a field. A new branch of mathematics was needed as a result. After utilizing these equations to summarize the behavior of electricity and magnetism, the mathematician Maxwell came up with a groundbreaking idea. What if, instead of a static electric field, a changing electric field generated a magnetic field? This interaction, he realized, would result in a wave of alternating electric and magnetic fields. Using vector calculus, Maxwell calculated the speed of this wave to be 310,000 volts. The symmetry of Maxwell's equations would show that the electric and magnetic fields are really two sides of the same force, was a huge scientific breakthrough in the 19th century. At the time, scientists thought they had found everything. They thought that Maxwell's equations and Newton's laws could explain all natural phenomena. However, at the beginning of the 20th century, a young scientist had many inquiries plagued his thoughts as he pondered the possibility of surpassing the speed of light. Albert Einstein, one of the greatest minds in history, posed a groundbreaking question. What would happen to Maxwell's equations if one were to travel at the speed of light? No one had ever thought about it before. Using Maxwell's theory, he calculated the speed of light from a moving object, such as a train, using Newtonian mechanics. He expected the speed of light to be the sum of the train's own speed. Just as if you had moved alongside a train, the result would have been the same. Newton's laws stated that you could catch up to anything if you moved fast enough, but Maxwell's equations showed that no matter how fast you traveled, you could never catch up to light. This realization was profound, and it led Einstein to challenge conventional ideas about motion and light. To his surprise, the light beam didn't freeze as expected. Instead, it continued moving at the same speed. This seemed impossible, since the speed of light can be measured using various devices, including clocks and meter sticks, and since this speed does not change regardless of velocity. Einstein postulated that space and time itself must distort in order to preserve this constant speed. This would explain why, for example, when traveling through space at high speeds, the onboard clocks would show a slower time than those on Earth. When we look at a spaceship traveling near the speed of light from Earth, it would appear as though everyone on board is moving at a snail's pace. The ship itself would also appear compressed and heavier, but to those on board, everything would appear perfectly normal. On the other hand, if you were to install an atomic clock on an airplane and compare it to one on the ground, the clock on the plane would run slightly slower by approximately 1 part in a trillion, because space and time can alter everything else, including matter and energy. The relationship between matter and energy is given by the equation E=mc². This formula answers a fundamental question in science about why the sun shines. It is believed that the conversion of some of the mass of hydrogen atoms into energy occurs under high temperatures, which is why objects become heavier as they move faster. However, the exact source of this extra mass is not known. In the midst of remarkable scientific progress, physicists have discreetly acknowledged an impending obstacle. The problem is that contemporary physics is predicated on 2 fundamental principles. The first is general relativity, put forth by Albert Einstein, which provides a framework for comprehending the cosmos at the most massive scale: stars, galaxies, clusters, and the enormous cosmos. The second is quantum mechanics, put forth by John Wheeler, which elucidates the cosmos at the most microscopic levels: molecules, atoms, electrons, and quarks. Although the predictions of both theories have been confirmed experimentally with remarkable accuracy, they lead to a troubling conclusion. As they are now formulated, general relativity and quantum mechanics cannot both be correct. Physicists choose to ignore the contradictions between the 2 theories because they focus on either small, light objects like atoms or large, heavy objects like stars and galaxies. However, the universe can be extremely dense inside a black hole, where enormous masses are. This first great physics disagreement occurred in the late 1800s when, according to Newton's laws, one could catch up with a beam of light if one moved quickly enough. However, Maxwell's laws of electromagnetism stated that this was impossible. Einstein eventually settled this conflict. In both instances, quantum mechanics and general relativity are necessary because they encompass both the extremely small and the tremendously large. In his theory of special relativity, which revolutionized our conception of space and time, Einstein demonstrated that nothing can travel faster than light. However, Newton's theory of gravity suggested that gravitational effects travel instantly across space. Einstein also resolved this conflict with his general theory of relativity in 1915, which demonstrated that space and time can bend and curve in response to matter. Energy transmitting gravity, space-time ceased to be static backdrops to the universe's operations but rather dynamic players. This pattern recurred. Just as general relativity solved one problem, it spawned another. In the early 1900s, physicists devised quantum mechanics to solve microscopic-level issues with 19th-century physics. The third and most significant conflict is between quantum mechanics and general relativity. In general relativity, the smooth curved space clashes with the. As a result of quantum mechanics' description of chaotic microscopic behavior, a new theory called string theory has emerged. This theory aims to unite all forces and phenomena in nature, from the tiniest particles to the biggest galaxies, using a single grand principle. The core of an atom is composed of quarks. A proton has 2 up quarks and 1 down quark, while a neutron has 2 down quarks and 1 up quark. The unique properties of each quark, in addition to the electrons that make up all matter in the universe, are determined by the specific combinations of these quarks. However, there is no evidence from experiments that these particles are. Neutrinos, which were predicted by Wolfgang in the early 1930s, are elusive, ghostly particles with such weak interactions with matter that they can pass through great distances unaffected. In fact, billions of neutrinos from the sun are passing through your body and the Earth every second. In the mid-1950s, Frederick Rains and Clyde Cowan presented definitive evidence for the existence of these neutrinos. Along with these, they found the tau, an even heavier relative of the electron, as well as two new neutron-like particles called the muon neutrino and the tau neutrino, which join the previously known electron neutrino. These particles are produced in high-energy collisions and have an extremely short lifetime, so they do not contribute to the matter we encounter in our everyday lives. Additionally, for every particle, there is an antiparticle, which has the same mass as the particle but opposite characteristics, like charge, for example, the tau neutrino. Scientists have discovered that antimatter is extremely rare in nature due to the annihilation that occurs when matter and antimatter collide. Particles can be classified into three different families, each of which contains two types of quarks, an electron and one of its heavier counterparts. One such family is the positron, which has the same mass as an electron but a positive charge instead of the negative one. Investigated matter at extremely microscopic scales, approximately 1/1000th of a meter, and found that all matter, whether it exists in nature or is synthesized in labs, is made up of a combination of particles from these families and their antimatter counterparts. This finding prompted many questions, such as why there are so many fundamental particles when the majority of them are neutrinos. Everything we observe relies solely on electrons, up quarks, and down quarks. But why aren't there four or more particle families? And what gives rise to such a wide range of masses? For example, why is the top quark over 40,000 times heavier than an up quark, or the toe particle over 3,500 times heavier than an electron? Are these numbers purely coincidental, or are they part of a larger scientific scheme? Things become even more complicated when we consider the forces at work in the universe. There are innumerable examples of objects interacting with one another. For example, a ball can be hit by a bat, and a nuclear bomb can detonate with tremendous force. One thing that all these interactions have in common is that they are based on the same four forces: gravity, electromagnetism, the weak force, and the strong force. Another thing is that objects can be crushed, pushed, pulled, shaken, or altered by freezing, heating, or burning. On a microscopic scale, every force originates from a unique particle, the tiniest component of that force. For instance, light emitted by a laser is actually a shower of photons, the smallest building blocks of electromagnetic force. Similarly, the weak and strong nuclear forces are carried by particles known as weak-gauge bosons and gluons, respectively. Scientists had demonstrated the existence of these particles by 1984. They also predicted a particle responsible for gravity, the tau. Scientists have measured these properties very precisely, but there's no clear explanation for why the universe contains these specific particles with their particular masses and forces. Similarly, the graviton has not been found yet, but another shared trait of forces is that, similar to how electric charge controls the electromagnetic force, particles also have strong and weak charges. Investigating the fundamental forces, despite their commonalities, leads to more inquiries. For instance, why are there only four basic forces rather than more or less? What makes their behavior distinct? Why are the strong and weak forces confined to microscopic scales, while gravity and electromagnetism operate over vast distances? The strength variations among these forces are puzzling. These aren't theoretical concerns. Even little changes in the characteristics of particles and forces, like the stable atomic elements, nuclei, rely on a delicate equilibrium between the strong force and the electromagnetic force. Protons' electric charges repel each other in the nucleus, but the strong force between quarks keeps them together. If this equilibrium were even slightly off, atomic nuclei would disintegrate. Similarly, if electrons were slightly heavier, they would combine with protons to form neutrons, destroying the most basic element, hydrogen, and preventing the formation of more complex elements. A crucial factor in stars is the strength of gravity. Stars like our Sun burn out at a much faster rate, which impacts the possibility of life. On the other hand, if gravity were weaker, matter wouldn't cluster in galaxies and stars wouldn't form. In short, the universe is structured the way it is because particles and forces have specific properties, but we still don't know why these properties are specific. This is where things get interesting. Intriguing string theory enters the picture to solve the riddles of elementary particles, which are now thought to be tiny point-like objects. According to string theory, if we could observe them with unprecedented precision, each particle would really seem like a tiny one-dimensional loop, like a microscopic vibrating rubber band. The properties of particles are a result of this string's movement and oscillation, which physicists have referred to as tiny. Building on our current understanding of particles such as atoms, protons, neutrons, electrons, and quarks, string theory postulates that the tiniest building blocks are actually vibrating strings. This theory presents a unified concept that all matter and forces are composed of these strings, and it offers a comprehensive framework for understanding the universe. It may also offer answers to the mysteries that have so far eluded us. Of quantum mechanics and general relativity, and more mathematicians and physicists are beginning to see it as a potential solution to these mysteries. When Einstein was formulating his theories, the only two recognized fundamental forces were electromagnetism and gravity. This left him wondering how two forces so different could coexist in nature. He rejected the idea that nature was constructed on such a complicated and apart design, and he embarked on a 30-year quest to discover what he referred to as a unified field. Looking back, Einstein was ahead of his time when he pursued Theory 1, which he thought would show both forces as different manifestations of a deeper principle. However, his pursuit separated him from mainstream physics, which was centered around quantum mechanics. Decades later, the search for a unifying theory has become one of the biggest challenges in modern physics. String theory suggests that particle properties like mass and charge are connected to the distinct ways. In this model, the fundamental strings vibrate in the same way that the strings of an instrument, like a violin or piano, produce different notes. In this model, every particle, like an electron or a quark, is said to originate from a particular vibration of a string. The same theory applies to the forces at work in the universe, as all matter and forces are thought to be different kinds of string vibrations. However, before we delve into the idea of strings, it's important to Introduction to Quantum Mechanics, which is equally important as the music. Quantum mechanics give a framework for comprehending the microscopic features of the cosmos, similar to how relativity changes our view of large, fast objects. Quantum mechanics reveals unexpected characteristics at the subatomic and atomic levels. And Einstein's revolutionary theories of relativity lead to reasonable conclusions once their principles are understood. However, quantum mechanics is distinct. By 1928, a mathematical framework was established that enables extremely accurate predictions to be made using quantum mechanics. However, the rules of the theory are often followed without a complete understanding of how they work. This is in contrast to relativity, which many people still find difficult to fully comprehend. Quantum mechanics, on the other hand, challenges our current understanding of the universe by exposing unexpected behaviors on atomic and subatomic scales. How can we make sense of this? The human mind, shaped by its everyday experiences, is unable to comprehend the mystic microscopic level. Could physicists have created a convoluted version of quantum mechanics that hides the reality behind it? No one knows for sure, but what we do know is that quantum mechanics reveals how many commonplace ideas become meaningless at the subatomic and atomic levels, making us reevaluate our language and reasoning to make sense of the universe at these scales. For example, according to Planck's law, the energy of a photon decreases as its wavelength increases. Using light with lower frequencies or longer wavelengths allows us to produce photons with less energy, which is great because the energy of a wave decreases with increasing wavelength. However, there's a limitation when using waves to determine an object's position. The precision of the measurement is limited by the wavelength of the wave. To put it another way, just like trying to find a rock beneath the surface, the accuracy of the measurement is equal to the wavelength of the wave. The ocean floor, by watching how waves alter when they encounter a rock. Up until they reach the rock, the waves are smooth, but as they go over it, they become distorted. By studying this distortion, you can only estimate the rock's position within a range defined by the length of the waves. In a similar vein, when measuring an object's position. With light, you can only get an accuracy that's roughly equal to the wavelength of the light. This is a trade-off in quantum mechanics. A more precise measurement of an electron's position can be achieved with high-frequency light, which has a short wavelength. However, this type of light is more energetic and can disrupt the electron's motion. On the other hand, low-frequency light, which has a long wavelength, has less of an effect on the electron but makes its position harder to pinpoint. Heisenberg found that there is a relationship between the two types of measurements, and that improving one makes the other easier. You can't know the exact location and speed of an object at the microscopic level using only one measurement. The more precise your measurement, the less precise your measurement of the other. This principle applies to all particles in nature, not just electrons. Einstein attempted to cling to classical physics by implying that despite quantum mechanics limiting our knowledge of, we used to believe that an electron's position and velocity were fixed, but recent decades of research by physicist John Bell and experiments by Elaine Aspect and others have shown that Einstein was mistaken. According to quantum mechanics, not only is it impossible to precisely measure both positions and speeds, but such a claim also contradicts more recent experimental results. It's as if, in a made-up universe where quantum effects are more noticeable, even inanimate objects like ice cubes in a drink would rattle around wildly due to this quantum claustrophobia, even though this is just a hypothetical situation. Imagine you've trapped an electron in a large box and then slowly shrank the box to pinpoint its location. The electron would begin to move around more wildly, almost anxiously, bouncing off the walls at unpredictable speeds. If you were to throw a small stone at a thick concrete wall, classical physics would tell you that it would bounce back because it doesn't have enough energy to break through, but quantum mechanics tells us that there's a tiny chance the pellet could actually pass through the wall. This happens because, in the real microscopic world, particles behave in this way. The more you try to confine them to a smaller space, the more erratic their motion becomes. This leads to an interesting phenomenon called quantum tunneling. In quantum mechanics, there is a trade-off in measurement precision. For example, Heisenberg demonstrated that you can't know a particle's position and velocity exactly, and the longer the measurement takes over short time, the more energy appears to fluctuate, giving the impression that the particle is briefly borrowing energy. This small but real possibility arises from the uncertainty principle. Permits phenomena, such as quantum tunneling, in which particles traverse insurmountable barriers. In classical physics, such a phenomenon would be extremely unlikely to occur with large objects, but it is theoretically feasible. After all, it would take longer than the age of the universe. A key principle of quantum mechanics is the uncertainty principle. Things that we typically assume, like the position, velocity, and energy of objects at any given time, are actually just effects of Planck's constant. Being tiny in our everyday lives, when this quantum insight is applied to space-time, it reveals problems with the structure of gravity, which is one of the biggest challenges in physics that has happened in the last 100 years. The pioneer of quantum mechanics concentrated on the Schrödinger equation and experiments, but he neglected special relativity. When he first attempted to incorporate it, the resulting equation didn't match experimental data on hydrogen. Instead of attempting to solve everything at once, he approached it piecemeal. Although he succeeded in developing a mathematical model for wave-particle duality, Schrödinger neglected to include special relativity in his early work. However, as time went on, physicists came to realize that special relativity is crucial to a correct quantum framework. After all, the fact that energy can take many forms, something that Schrödinger's model failed to account for, led to the development of quantum electrodynamics, relativistic. Uncertainty and probability are fundamental to quantum mechanics, and the theory's incorporation of quantum concepts into the classical idea of a force field, such as Maxwell's electromagnetic field, makes it a field theory. In a quantum field, for example, instead of discrete particles like photons, there are invisible field lines that carry energy as they vibrate through space and time. The gluon and weak boson constituents of the strong force, as well as the W and Z bond constituents of the weak force, are elementary particles devoid of internal structure. They transmit their respective forces, much like the matter particles in the model. For example, in the case of electrically charged particles repelling each other, it is not merely the field surrounding them at work, but rather the particles exchange photons, much like two skaters pushing each other by throwing objects back. When two charged particles exchange photons, the force is attractive. However, photons do not directly transmit the force. Instead, they send a message to the particles, instructing them to move apart for like charges and together for opposite charges. This is why photons are referred to as messenger particles for the electromagnetic force. The ice skater analogy has a flaw in that throwing bowling balls always pushes the skaters apart. Given the success of quantum field theories for the other three forces, one could propose a similar theory for gravity using gravitons as messenger particles. This idea seems appropriate because there are intriguing similarities between gravity and the other two forces, and gluons are the messenger particles for the strong force that holds quarks together inside protons and neutrons. Weak gauge bosons mediate the weak force, which is responsible for particle transformations in radioactive decay. All observers, regardless of their speed, are equal under the gravitational force. In fact, even those going at high speeds can pretend to be at rest by directing the force's energy into a gravitational field. This forces symmetry, just as the strong, weak, and electromagnetic forces do, though these are more abstract than gravity. To illustrate the principles of subtle symmetry, consider the fact that quarks come in three colors: red, green, and blue. This type of symmetry, where physics remains unchanged by color charge shifts, is known as gauge symmetry or the strong force. It's important to note that, similar to how electric charge affects electromagnetic interactions, data shows that interactions between quarks of the same color are identical as are those between different colors. This holds true for both strong and weak forces. From an observational standpoint, gauge symmetries also require specific forces. Hermann Weyl, Chen-Ning Yang, and Robert Mills demonstrated that these forces must be strong enough to maintain physical interactions unaltered regardless of changes in the charges of quarks and color charges. Similar to how the weak and electromagnetic forces are connected to their respective. The four fundamental forces are all connected to principles of symmetry through their own gauge symmetries. Since all four forces are similar, many physicists believe that gravity should also have a quantum field theory, just like the other three. However, this has proven to be a difficult goal to achieve, as general relativity is effective at large astronomical distances, when space looks flat without mass, and combining it with quantum mechanics necessitates. When we look at space from a microscopic perspective, it looks flat at first. However, when we dig deeper into space, we see that it is actually subject to fluctuations caused by the uncertainty principle. These fluctuations cause the gravitational field to undulate, which leads to severe distortions as we focus on smaller and smaller scales. Finally, at the most microscopic scales, space becomes a chaotic, turbulent quantum foam, a concept introduced by John Wheeler. This quantum foam represents a fundamental clash between general. When we combine the equations of general relativity and quantum mechanics, we often get infinite results, which indicates that there's an issue with our approach. On the one hand, general relativity has trouble dealing with the chaotic nature of quantum foam. On the other hand, as we move to larger distances, these small-scale fluctuations average out, and the universe appears smooth. Just like how a dot matrix picture appears smooth from a distance, but is actually composed of individual dots up close. General relativity is able to accurately depict large scales, but its smooth geometry collapses at tiny scales as a result of quantum fluctuations. Using this information, we can calculate the minuscule distance scale at which their incompatibility becomes apparent, with a plant length of approximately 10 to ⁻³ 33 centimeters, which is much smaller than anything we can easily comprehend. To put it in perspective, if an atom were magnified to the size of the sun, despite many attempts to reconcile general relativity and quantum mechanics, some physicists are troubled by the basic incompatibility of these core theories and continue to use them for larger scales, even though the Planck length would be about the height of a tree in this universe. Ultimately, we should have a consistent and unified understanding of the universe, not a mix of conflicting frameworks. Until the advent of superstring theory, solutions to the problem of quantum mechanics remained elusive. According to this theory, the point-light particles of the Standard Model are actually very small vibrating loops of string, with a typical length around the Planck scale about 10 times smaller than an atomic nucleus. Since present experiments are unable to detect such minuscule strings, this finding should come as no surprise. Before we delve into the intriguing implications of substituting strings for point particles, let's take a step back and ask, what are strings made of? The first possibility is that strings are incredibly basic, like the uncuttable atoms of ancient Greece, and the second is that they're the tiniest possible particles. To observe them directly, we would need a particle accelerator that is millions of billions of times more powerful than anything we have built thus far. In this view, strings are the fundamental building blocks of the universe. They are not composed of anything smaller, as that would make them less fundamental. The second answer recognizes that we don't know if string theory is the final word on the nature of reality. If it's incorrect, then strings may not be fundamental at all. However, history shows that with each deeper understanding, as our knowledge of the universe expands, we find ever tinier pieces. This leads us to wonder if strings are simply an additional layer, perhaps composed of even smaller structures. While there are theoretical suggestions that strings may have substructure, no conclusive proof is available at this time, and additional research is required. Instead, let's pretend for the sake of simplicity that strings are the most basic building blocks of particles. The Standard Model of particle physics, which originally included the two main components, bosons and fermions, has. While the Standard Model can predict interactions based on measured data, it fails to explain two major shortcomings. First, that it doesn't account for gravity, and second, that it doesn't provide a deeper rationale for why these particular particles and forces exist, or why the 19 parameters that characterize them have their specific values. This leaves the universe's properties feeling arbitrary, as if they could have been different by chance. In contrast to other theories, string theory only needs one key input, a number that establishes the scale for measurement, in order to explain all properties of the microscopic world. To understand this, consider the familiar violin strings, which can vibrate in an infinite variety of patterns to produce different musical notes. Similarly, in string theory, the strings can be easily adjusted to different particle configurations if experiments had shown them. A particle's mass and the force charges it exerts are determined by the fundamental string's vibrations, which in turn are determined by the particle's mass. The relationship between the mass of the particle and the vibrations of the string becomes more apparent when one considers the energy of the string. The vibrational energy of the string is dependent on the amplitude, which is the height of the vibrations, and the wavelength, which is the distance between the peaks. In string theory, heavier particles have strings with more energetic vibrations, greater amplitude, and shorter wavelength. On the other hand, lighter particles have strings with less energetic vibrations, and longer wavelengths and smaller amplitudes mean less energy. This is analogous to how, when you pluck a violin string harder, the vibrations are more intense, while when you pluck it softer, the vibrations are gentler. This relationship between energy and mass is explained by special relativity. Physics has shown that the way a string vibrates determines the electric weak and strong charges of a particle. This holds true not only for matter particles like ICs, but also for force-carrying particles like gluons, photons, weak-gauge bosons, and gravitons, among others. Notably, one of these patterns corresponds to the graviton, meaning that gravity is intrinsic to all of them. According to string theory, elementary particles derive their properties from the unique vibrational patterns of their internal strings, much like different musical instruments. This is a significant departure from previous perspectives that held that different particles were composed of different substances. For instance, electrons were believed to have a negative charge and neutrinos to have none. Instead, string theory proposes that all particles are composed of the same type of string, and that the variations between them result from these differing patterns of vibration. since the forces between these fundamental strings can describe all physical events and processes in the universe. String theory offers the potential for a single comprehensive description of the physical universe. The theory of everything is based on this principle, which is similar to how everyday strings like violin strings or shoelaces have different tensions. In other words, the universe is like a cosmic symphony of vibrating strings. Since these particles are too small to be measured directly, scientists have turned to indirect methods. In 1974, Shirk and Schwartz put forward the idea that the vibration pattern of a single string represents the graviton, the particle responsible for gravity. Their calculations revealed that the force of gravity is connected to the string's tension, which is incredibly high at about 139 tons, known as the Planck time. As a result, fundamental strings in string theory are noticeably stiffer than the strings commonly used in instruments like the violin or the piano, and they are significantly larger than the typical string gauges. They contract to a small size of approximately 10 carat, 33 centimeters, which is the length of the Planck. The high tension gives the strings a lot of energy, just like tighter strings on an instrument. Strings with more tension can't vibrate as easily, but they retain more energy than strings with less tension, even when they do vibrate. The energy of a vibrating string is determined by two factors: the pattern of vibration. More complex patterns mean more energy, and the string's tension. You would think that lighter vibrations would reduce the string's tension, but that's not always the case. Einstein's formula E equals mc squared states that the smallest energy levels are enormous, measured in multiples of the Planck energy. However, according to quantum mechanics, energy does not exist in a continuous form. Rather, it is always a whole number multiple of a minimum amount that depends on the string's tension and the number of peaks and troughs in its vibration. The Planck mass, which is approximately 10 to the carat 19 times that of a proton, is comparable to a grain of dust or 1 million bacteria. According to string theory, the usual mass of a vibrating loop is a whole number multiple of the Planck mass, called the Planck scale. This begs the question, how can string theory account for much lighter particles like electrons, quarks, and photons if its natural energy scale is so much higher than a proton? The answer to this question is found in quantum theory. Nothing is ever totally still in mechanics because of the uncertainty principle. This includes strings in string theory, which can experience quantum vibrations. Interestingly, these quantum jitters can cancel out some of the vibrational energy of the string, reducing it by an amount close to the Planck energy. This leads to lower energy vibrations, which are consistent with particles with much smaller masses, as seen in particle physics. For example, Shirk and Schwartz discovered that the graviton vibrations cancel out perfectly, leading to this massless particle mimics the behavior of the gravitational force, but the majority of string vibrations are caused by much heavier particles, much heavier than a proton. So, the light particles we see are actually the result of complex energy interactions between strings. Even a heavy particle, like the top quark, which is 189 times heavier than a proton, can only form if the string's enormous Planck scale energy is canceled out with incredibly fine precision, better than 1 part in 100 million billion. It's like being handed an enormous sum of money and requiring the exact amount of $189 to be spent. It is practically impossible to accomplish this task. String theory calculations indicate that energy cancellations of this kind can occur, but confirming them with absolute precision is beyond our present knowledge. Nevertheless, many properties of string theory, which are not dependent on these minute details, can be studied with confidence. Additionally, strings can vibrate in an infinite variety of patterns, which raises the question of whether this variety indicates an infinite number of particles. In line with string theory, which posits that every possible vibrational pattern of strings corresponds to a distinct particle. However, due to the high string tension, the majority of these patterns generate particles that are much heavier than the Planck mass. As a result, only a small number of low-energy patterns correspond to particles that are lighter. Unfortunately, our particle accelerators do not have the power to detect these lighter patterns. Heavy particle searches in labs are currently out of the question, but there are indirect ways to find them. One such way is to look at the early universe, when the Big Bang was happening, when the energies were high enough to create these particles. Of course, most of those particles would have decayed into lighter ones by now, but there's always the chance that one has survived. If so, finding it would be a groundbreaking discovery. String theory is appealing because it helps resolve the conflict between quantum mechanics and gravity. The problem arises because general relativity fails because it assumes that space and time are perfectly smooth, but quantum mechanics reveals that everything, including space and time, is subject to minute chaotic fluctuations. These fluctuations become so strong at extremely small scales that they disrupt the smoothness of space, leading to the collapse of general relativity. String theory provides a solution by reducing the quantum fluctuations and smoothing out space at very small distances, thereby easing the conflict between the two theories. Particle accelerators use subatomic particles, such as protons or electrons, to probe atomic and subatomic structures because larger objects, like half-millimeter pellets, cannot reveal such fine details. Here, quantum mechanics comes into play, and the sensitivity of a particle as a probe is measured by its quantum wavelength. This wavelength represents the uncertainty in the particle's position, as explained by Heisenberg's uncertainty principle. The smaller the relationship between a particle's energy and its wavelength is inversely proportional, meaning that higher energy particles have smaller wavelengths and can reveal finer details. This means that higher energy particles can explore smaller, more detailed structures, which is different from point particles and strings. Just as plastic pellets are too big to reveal fine details, strings are too small to explore structures that are smaller. In 1988, David Gross and Paul Mina demonstrated that, in contrast to point particles, strings initially benefit from higher energy when probing smaller structures. However, once the string reaches the Planck scale, further energy causes it to grow larger, decreasing its sensitivity to small details. As a result, while point particles can probe smaller areas with more energy, strings grow too large to investigate minute structures regardless of their energy content. The disagreement between general relativity and quantum mechanics arises from the interaction of space at incredibly small sub-Planck length scales. If the fundamental units of our universe, the strings, cannot traverse distances smaller than the Planck length, they will not be impacted by the chaotic quantum fluctuations occurring at such minuscule scales. This is analogous to running your palm across a smooth surface, even though the granite is microscopically rough. Comparing the surface of granite to the fabric of space in string theory, the main difference is that while we can use tools like electron microscopes to examine granite's tiny crystals, strings are too large to detect the tiny fluctuations in space, so they smooth out the chaos. This smoothing also resolves the clash between general relativity and quantum mechanics and eliminates the problematic infinities that arise when using point particles to explain gravity. String theory has a fundamental limit before quantum effects take over. So these extreme fluctuations don't exist in the string theory universe because they can't be measured. You might be dissatisfied because it seems like string theory avoids dealing with sub-Planck length fluctuations by focusing on the string's non-zero size. But in reality, it does reveal sub-Planck scale imperfections in space. Solve the problem. Firstly, the problematic fluctuations arise from the fact that physics is based on point particles. However, according to string theory, there's a limit to how far we can explore the cosmos, which eliminates these fluctuations. Secondly, although physicists such as Pauli and Feynman proposed that particles aren't points but rather small blobs, they were unable to reconcile their ideas with basic principles. String theory reconciles this, while also accounting for gravity. This simplified explanation shows why string theory succeeds where point. Since we've already covered special relativity, we can go on to discussing how string theory smooths out quantum fluctuations. One way to look at it is as a contrast to point particles, which collide and scatter like billiard balls. Strings, on the other hand, blur the information gathered at very small scales, solving the problem of short-distance behavior in physics. To put it simply, think of an electron colliding with its antimatter counterpart, a positron. When these two types of matter come into contact, they can annihilate, releasing energy in the form of a photon. This photon then travels and recombines with an electron and positron, creating a new pair of particles. This process is analogous to the way in which two billiard balls collide. At exactly the right moment, the electron and positron will collide, annihilate, and produce a photon. However, if we visualize these particles not as points, but as one-dimensional strings, the process is the same, but with oscillating loops instead of points. When the strings vibrate at the correct frequencies, they behave like electrons and positrons. When these strings collide, they merge into a single string, the photon, and then split into two new strings. From a larger vantage point, this still resembles the point-particle interaction. The main distinction between the two is that the collisions of point particles happen at a specific time and place, while string interactions split into two new strings. It's interesting to note that when it comes to strings, observers tend to agree on certain details. However, when it comes to point particles, the entire interaction occurs at a single point in space, and this can lead to disagreements about the exact time or place where the strings first touch. To illustrate this point, consider slicing a loaf of bread. One observer may perceive the strings getting closer, and that observer's perception of the moment they first touch will be at a specific time. In the case of gravity, where gravitons are involved, the concentration of force can lead to problems and infinite results if not handled properly. String theory, on the other hand, spreads out the interaction across a larger area, so that different observers see it happening at different points, effectively reducing the intensity at very small scales and replacing them with manageable finite results. This smoothing also removes the jitteriness of space at sub-Planck scales. In string theory, the finer details that would be detected by point-particle theories are muted and rendered insignificant, much like looking through a pair of blurry glasses. This is because, according to string theory, there is no way to resolve the inherent conflict between general relativity and quantum mechanics at such incredibly small scales. Instead, the laws of large and small scales are able to coexist harmoniously. Ultramicroscopic strings are special for two reasons. First, they can be described in terms of quantum mechanics, even though they are extended objects. And second, their vibrational patterns are identical to those of gravitons, which means that they intrinsically contain gravity. Since string theory postulates that point particles are merely mathematical idealizations, this begs the question, could strings also be idealized as infinitely thin, or could they actually have a certain thickness like a thin tube or donut? Physicists such as Heisenberg and DRA have previously attempted to construct a theory involving three-dimensional objects, but their efforts have been met with significant obstacles. However, in the mid-1990s, string theorists made the surprising discovery that higher-dimensional objects are an integral part of string theory. It became evident that string theory encompasses more than just strings. It also incorporates various components of different dimensions, such as two-dimensional shapes resembling frisbees and three-dimensional blobs. These insights were introduced during the We can be persuaded, through a combination of theoretical necessity and experimental limitations, that there are extra curled-up spatial dimensions. This idea was initially put forth by Kusa and later developed by Klein, who hypothesized that the universe might contain dimensions beyond our three-dimensional experience. These extra dimensions could be so tiny and tightly curled up that they elude detection by our present-day instruments. On the other hand, the concept of extra dimensions might appear unrealistic, particularly in light of the fact that we currently can't probe depths less than a billionth of a meter, which opens the door to all sorts of fantastical possibilities, including small green alien civilizations, while extra dimensions appear more reasonable. However, since neither of these ideas can be tested at the moment, string theory is changing people's perceptions. IT solves the central problem in modern physics, the disagreement between general relativity and quantum mechanics, and unifies our knowledge of the fundamental laws of nature. Particles and forces. In order to accomplish this, string theory necessitates additional spatial dimensions. According to quantum mechanics, our predictions can only be based on probabilities that are always between 0 and 1. If, however, our calculations produce probabilities that are outside of this range, such as infinite or negative probabilities, it indicates a problem with the theory. At first, string theory appeared to have these problems, but physicists worked intensively to determine the source of the problem, which occurs when a string is limited to a two-dimensional surface. Strings can only vibrate in two directions when they are close to the surface. However, if they can move away from the surface, they gain a third direction, greatly expanding the possibilities for vibration in a multidimensional universe. This is vital to the success of string theory, as physicists have found that calculations involving strings only work correctly when they can vibrate in 9 spatial directions. Otherwise, errors such as negative probabilities arise. At one point, this idea prevented string theory from being written off as irrelevant, even though calculations reveal that the universe has a total of 10 dimensions, including 9 spatial ones, according to physicist Ernest Rutherford. This is because, in addition to the 3 large spatial dimensions that we experience, there may be 6 smaller, curled-up dimensions. I find it intriguing that in the mid-1990s, new research proposed that string theory actually requires 10 spatial dimensions plus time, for a total of 11. My question is, why are 3 of these dimensions big and extended, while the others are small and curled up? Is it because they aren't all the same? At the moment, we don't know the answer to this question. It has been suggested that all dimensions began curled up, and then, in a big bang-like event, 3 spatial dimensions and 1 time dimension expanded to their current size while the others remained small. Some rough ideas have been put forward to explain why only 3 spatial dimensions expanded, but our understanding of string theory isn't advanced enough to do so just yet. Current research aims to prove that the theory itself assumes only 3 dimensions are extended, since that's what we observe. If string theory does in fact require additional dimensions, could some of those dimensions be time dimensions rather than space ones? This idea may sound strange, but we're used to the concept of multiple space dimensions since we live in a world with 3. So what does it mean to have more than 1 time dimension? Isn't it strange that one dimension acts like the time we know it to, while the other operates differently? Things get even stranger when we picture a curled-up time dimension. For instance, if an ant were to walk around a curled-up space dimension, it would eventually end up back where it started. This makes sense, given that we can always return to the same spot in space. But if time were curled up, then traveling through it could mean visiting a past moment. Something we never really experience, seeing as how time only ever seems to advance without ever allowing us to go backwards. It's conceivable that additional time dimensions function differently from the familiar one. If so, this would fundamentally alter our conception of time. Currently, researchers in string theory are exploring this possibility, but no definitive answer has been found. Therefore, for the time being, we will continue to assume that all extra dimensions in string theory are spatial, though we may revisit the possibility of additional time dimensions in the future. Strings, despite their diminutive size, have a profound impact on the physical laws we observe in string theory. This relationship is especially apparent when considering that the masses and charges of particles in string theory are dictated by the ways in which the strings can vibrate. To illustrate this point, consider how ocean waves in open seas, which are as free to move in any direction as a string in large open dimensions, behave differently when they pass through a narrow area, such as a canal. Similar to how water depth and rock shape impact their movement, the size and shape of musical instruments like an organ pipe or a French horn determine the specific sounds produced by the air vibrating inside the instrument. Similarly, the geometry of extra curled dimensions affects the possible vibration patterns of strings, as strings vibrate through all dimensions. The properties of particles, such as their masses and charges, are determined by the microscopic vibrations of tiny strings that make up the universe. According to string theory, there are additional dimensions of space that are curled up so small that we cannot see them. However, Those strings can move through these tiny spaces, and as they do so, the masses and charges of particles are observed in our familiar three-dimensional space. String theory research aims to understand the geometry of these curled-up dimensions, which impact the vibrations of the strings and, by extension, particle properties like mass and charge. However, the extra-spatial dimensions in string theory cannot be shaped arbitrarily because the theory's equations impose strict limits on their possible arrangement. Although the mathematics underlying collabo spaces is complex, we can obtain a good idea of their appearance through visual representation. However, it is important to note that attempting to display a six-dimensional shape on a two-dimensional surface leads to distortions. There are numerous varieties of Calabi-Yau shapes, but they all serve the same purpose. The number of possible shapes is infinite, but rare. To summarize, think of a Calabi-Yau space instead of the two curled-up dimensions. This would mean that there are 6 additional dimensions, all tightly curled into complex shapes, present at every point in our familiar 3 dimensions. These additional dimensions are everywhere. For example, when you move your hand in a big arc, you're actually moving through all 3 dimensions, not just the familiar 3, but also these tiny curled-up dimensions, because they are tiny, so tiny that you pass through them ad nauseum, so tiny that when you move your hand, you don't really feel the tiny journey through these extra dimensions. Music. Some critics of string theory say that it's all just talk, that it predicts too many universes, and most importantly, that it can't be tested. The idea of string theory captivated a famous astronomer named Kepler, who was once led astray by the allure of beauty in science. It was once believed that the solar system appeared like a nest of regular shapes, resembling Russian dolls. This notion, which had its origins in ancient Greek geometry and drew inspiration from cubes and pyramids, appeared lovely at the time, but it has since proven to be entirely wrong. More recently, however, a number of physicists have cast doubt on string theory, claiming that aesthetics alone cannot lead us to the truth in physics. Paul Dirac, a renowned physicist, shared this view. He believed that the pursuit of mathematical beauty was essential to theory development. And it was through this pursuit that he came up with his famous theory of the electron, which relied on pure mathematics rather than experimental data. Nevertheless, as physicist Sabine Hossenfelder pointed out, many aesthetically pleasing theories regarding unified forces, new particles, and other concepts have been proven incorrect. String theory has been criticized for being untestable due to the extremely high energy required to test it. For instance, the energy of gravitons according to string theory is 4 times greater than what the Large Hadron Collider, LHC, can produce. Constructing an LHC 4 times larger would require a particle accelerator the size of a galaxy. Furthermore, each solution in string theory describes an entire universe, and there may be an infinite number of them. String theory appears to be difficult to test directly due to the large number of these universes. However, proponents of the theory remain optimistic, arguing that indirect evidence, such as studying solar light or remnants of the Big Bang, could provide indirect support for the theory. For instance, astronomers have recently found that only approximately 5% of the universe is made up of dark matter, composed of regular atoms. The remaining portion is dark matter and dark energy. Dark matter, accounting for approximately 27% of the universe, is unseen but influences galaxy motion. Dark energy, constituting approximately 68% of the universe, is even more enigmatic and causes galaxy separation. Some speculate that these unseen components may hold secrets regarding string theory. It's important to note that critics play a critical role in thoroughly testing and questioning theories, regardless of their quality. Finally, we hope you've enjoyed and learned something from our video. If so, please consider subscribing. It's completely free and would much benefit our channel. Thank you for watching, and until next time.